Hi everyone. In this video we are going to finish talking about the real zeros of a polynomial function. This is part 6 of all of our series on this, and we've done all these previous objectives, and now we're going to do the last one, which is to use the intermediate value theorem. So the intermediate value theorem says the following: if f is a function that's a polynomial function, and if a is less than b, and then if f of a, meaning this y value when you plug in a, and this f of b, y value when you plug in b, if they have opposite signs, so one's negative and one's positive, then there's at least one real zero of your function in between them. And so here's just two images of examples for this theorem, and essentially it's because if you have a polynomial function, if you draw the graph, it's continuous and smooth. You're not going to pick up your pen when you draw it. So if you know that one of your y values is negative and the other one is positive, then somewhere in between, depending on what happens with your function, but somewhere in between those two numbers, you're going to hit the x-axis. You're going to have a y value of 0. Sometimes there's more than one, like this example here. Okay, so let's use this theorem to just show that the function f of x, given here, has one real zero between the numbers 0 and 1. Okay, so we're just showing that this function is going to have a 0, something equal to 0 when we plug it in, between the x values, these are both x values, of 0 and 1. Okay, so if we plug in 0 and 1 into our function, 0 gives us negative 1 as a y value, and 1 gives us 2. And then we can just say, because of the intermediate value theorem, since this y value is negative and this y value is positive, then somewhere in between we're going to hit the x-axis, and so there's a real zero in between them. So just as an image for you, if you were to plot those 2 points, we have f of 0 is negative 1, which is this point here. F of 1 is 2, which is about right here. If I put some tick marks for you, let me put those. Then somewhere in between, our function has to do something to where it hits the x-axis right here. So there's a real zero in between. So that's all that we needed to do here, is just show that there's a zero in between those two numbers, and there is. Okay, so now how do we actually find that zero? We know it exists somewhere in between 0 and 1, but what is the value of that 0? What is that x number? Here's a process for approximating the 0. So step 1, find 2 consecutive integers for which there's a real 0 between them. That's using our intermediate value theorem. On the last example, that was 0 and 1. And then what you want to do is divide that interval between the number and the second number into 10 equal parts, 10 equal sub-intervals. Then evaluate your function at the endpoint of each subinterval until you see that the sign changes. So pretty much you're looking for the intermediate value theorem to come into play again. And so then you know there's 0 there. Then you start repeating. So then divide the new interval into 10 equal parts and repeat until you get the desired accuracy that you want. And so we're going to go through an example so you see this. And so note on step 3, once you find the value of f, if you actually get that it equals 0, then you're done, because that's what you're looking for. You're looking for f of what number equals 0. Okay, so let's work this out. Using our previous polynomial, we're going to find the positive real 0 accurate to 2 decimal places. Right, so from the previous example, we already know that we should be looking between the numbers 0 and 1. And so using our process we just talked about, we're going to divide the subinterval from 0 to 1. So this looks like, if I think of my x-axis, 0's here, 1's here, and 2's here, and so on. I'm cutting this interval into 10 subintervals. So I'm cutting this into 10 equal parts. Okay? And then I'm going to check each of those intervals for to narrow down where my 0's at, for using the intermediate value theorem again. Okay, so here's the new subintervals. It's going to be from 0 to 0.1, from 0.1 to 0.2, and so on. Okay. Now, let me just show you really quick how you would get these values. These numbers are not too bad. Between 0 and 1, we know that it's just 0.1, 0.2, and so on. But what you do is you take your larger number, in this case 1, you subtract your bigger number, or sorry, smaller number, and then you divide that by 10. And that's how you're going to get all of these points, how large the intervals are. Again, for 0 and 1, it's not too bad. It's always 0.1, 0.2, and so on. Okay, so then we're going to check each of the endpoints on these intervals. So we're going to check 0, we're going to check 0.1, 0.2, 0.3, all the way until we get back to 1 here. Alright, so we plug in 0.1, 0.2, 0.3. So far, all the answers when we plug those into our functions are all negative. That's what we're looking at. When is the sign going to change? Because that means we crossed the x-axis when it changes. Plugging in negative 4, 0.4, plugging in positive 0.4, 0.4, 0.5, 0.6. These are all still negative. Plugging in 0.7. Oh, okay, look at this. At 0.8, this is where it changed to positive. So this is where we stop. We don't have to plug in 0.9 because between 0.7 and 0.8, something happened. When we plot the points on our graph, we crossed over the x-axis because we went from having something negative, a negative y value, to a positive y value. So we want to look between 0.7 and 0.8. Alright, and so then now we repeat the process. So now between 0.7 and 0.8, we need to divide that into 10 equal subintervals. So in this one, you would have the larger number 0.8 minus the smaller number 0.7. Divide that into 10 equal parts, and you're going to get that those are going to be the length of 0.01. And so from there, what you would do is you would say, okay, I want to look at 0.70. Then the next interval would be 0.7 to 0.71. Then after that, it would be from 0.71 to 0.72, 0.72 to 0.73, and so on. And so that's what that's saying. And so if you begin, if you check your endpoints of all those new subintervals, we don't have to look too far because pretty quickly we have that at 0.70, this is negative, but the very next number, when we plug in 0.71, this is positive. So that means there is a 0 in between these two numbers. So the 0 we're looking for is somewhere between 0.70 and 0.71. And so the question only said to go to 2 decimal places, so we don't have to repeat the process anymore. If it said go to 3 decimal places, we would keep repeating, but we're good to go because this is as accurate as we want to get on this one. And so the 0 of our function lies somewhere between 0.70 and 0.71. And so if we have to choose one, we're going to choose to round down to the lower one. And so the 0 we'll say is approximately 0.70. And just so you know, if you plug that back into your function, which we have written already here, you're going to get that it's not exactly 0. It's negative 0.02 and 98. So it's really, really close to 0. And if we were being more accurate, then we would get numbers that were even closer. So that if we were to keep going, we would get something like 0.00 something. And so on. If we kept going, 0.000 something, and that's so we would get even closer to the actual number. But this is the process for using the intermediate value theorem to approximate the 0 of a polynomial function. Okay, that's it. Thanks for watching.